Welcome to EDU World Space.
The RC circuit shown in this diagram is called a high-pass filter because it allows high-frequency A signals to pass by with lower attenuation than with low-frequency signals. So high-frequency signals will pass through while low-frequency signals are blocked out. We want to show that the voltage gain, which is equal to the voltage
Here's a clean
output
and professionally formatted
or the voltage
presentation of
in,
the calculation shown in
where
the
voltage
image.
in is provided by our power source. We want to show that this is equal
Application
to
of the work energy
2 pi
theorem, WET.
times the
From the work
frequency
energy theorem,
times the
the force
resistance
F is given
times the
by F
capacitance
equals frac tex KE,
all over
where KE
4
equals kinetic energy,
pi squared,
S equals stopping distance.
frequency squared,
I'm given
resistance
for object
squared,
A, FA equals frac
capacitance squared
100,000,
plus 1,
0.10.
all square
For
rooted.
object B, FB equals
So how
frac
do we show this?
225,
Let's start
1500,
by
or
finding the
0.15
voltage
tex
output
makes N.
across the
And force
resistor.
ratio frac FA,
So using a
FB
voltage divider
equals
equation,
frac
we can
0.10,
show that this is equal to
0.15 equal
the
frac 2 null
resistance
result. A box
over
frac FA,
the total
FB.
impedance of the circuit,
Would you like a PDF
which
version
is
of this
R squared
explanation?
plus the reactance of the capacitor squared square rooted. And all this times the input voltage. So this tells us the ratio of how much voltage is dropped across the resistor, which is what we want to find. So this ends up being equal, simplifying the expression for the reactance of the capacitor, to the voltage input times the resistance over square root of resistance squared plus 1 over 2 pi times the frequency times the capacitance squared. And as I said, all this square rooted. So now simplifying further, we get 2 pi frequency, capacitance, resistance times the input voltage all over the square root of the resistance times the capacitance times the frequency times 2 pi plus 1, where this bit is squared and this entire denominator is square rooted. So now we simply divide this in the denominator of V output. So we take V output and divide it by this expression, and we finally show that A is equal to 2 pi FRC over 4 pi squared, frequency squared, resistance squared, capacitance squared, plus 1, all square rooted. Great, so we've successfully shown that the attenuation is given by the expression we expected. So now we want to discuss what the behavior is as the frequency goes to 0 and the frequency goes to infinity. So the frequency goes to 0, we can see that the gain will also drop to 0 because we have a frequency in the numerator here, but our denominator will stay finite. So in this instance, the capacitor becomes fully charged and no current will flow across the resistor because all the voltage will be dropping across the capacitor. So the output voltage will drop to 0 across the resistor. Now let's look at the behavior as the frequency becomes very big. So as the frequency goes to infinity, the capacitive reactance becomes very small, which allows for a large current. So in the case of a large current, most of the voltage drop will drop across the resistor rather than the capacitor, and the capacitor will not have time to be fully charged. So in summary, as F goes to 0, the voltage drop across the resistor also goes to 0. And as the frequency goes to infinity, the voltage drop across the resistor becomes maximized. So in the final part of this question, we're given specific values. So let's pop over to a new page. So we're choosing our resistance to be 850 ohms, our capacitance to be 1 times 10 to the minus 6 farads, so 1 microfarad. We want to plot a graph of the logarithm of A versus the logarithm of F, the frequency. So we want log A over log of F. And we can be a little precise in how we graph this, but just to show qualitatively what the behavior looks like, we want to mimic the behavior that we just discussed in part B. And that'll look like as frequency increases, so too should our A factor But at a certain point, we'll maximize and reach a value where our voltage source is completely saturated. So as we can see, this behavior is representative of a high-pass filter because higher frequencies are passed through while low frequencies are completely attenuated out. So that's the answer to this question.